My name's Joe Barnard. I build model rockets that use active control via thrust vectoring. In the last 2 years, I have given presentations at this conference and talked mostly about what I have done. And that's cool, that's all well and good, but at some point, you just don't need to feed the ego anymore. So I figured, since in the last year or two, there have been a couple of projects that have gotten started that are trying to do similar things. This stuff is really cool, and man, I totally love that. So there are a bunch of people who are trying to do similar things, and I figured if I could lay out some type of roadmap to give people a sense of where you can go, if you don't know anything about this and you want to get started, what does it sort of look like? What does this whole project look like if you want to take it on yourself? It's a little harder to get to something like that, but I wanted to sort of see if I could simplify it a bit. So let's get started with the real basics. I'm sorry this is cut off here. I'm not sure what's going on.
It's wrapped.
Oh, geez. Is it going to be okay?
Yeah.
Should we leave it?
Yeah, go with it.
Okay. So what is thrust vector control? Is it a thing you can hold? Can you give it to a friend? Can you throw it off a cliff? No, you cannot. It is a technique, not a physical thing. And so it is a technique that we use in the aerospace industry to stabilize craft. Sometimes they are airplanes, fighter jets, sometimes they are rockets. And so let's just walk over how that works. I've got some little animated drawings here. Here's my BPS rocket. And when we zoom in on the bottom of it, you'll see that we have a thrust vector going down. It's just a vector, it's an arrow. And then we have a reaction force vector going directly upward. That's when everything is going well. And right on over here, when things are going a little sideways, we have a thrust vector that's going to the side, and what ends up happening is we resolve two force vectors. One is going vertical, and then we've got a tiny little one going to the side. And so when we talk about thrust vector control, that little arrow is what we're talking about. It's not a thing you can hold, it's not a thing you can give to a friend. So that little arrow is what we're talking about. So how do you do it? How do you accomplish TVC in any scale? What I like to do is gimbaling the motor, and by that, you put the motor on a dual axis hinge. So the motor can hinge to the side, it can hinge up or down, and by that, you change the vector of the thrust. But you can also do it with the nozzle of the motor. This is the Space Shuttle SRB, solid rocket booster, and this is some sped up footage of it vectoring the nozzle during a ground test. These are jet vanes that are used on the V2 rocket, and so by putting small fins into the exhaust stream, you can deflect them and change which way the exhaust goes. This is footage from Copenhagen Suborbitals of their jet vane approach. It's pretty cool. This is pretty incredible footage. The other approach you can use is called LITVC, and though the screen is cut off here, this is from the Boston University Rocket Propulsion Group. LITVC stands for Liquid Injection Thrust Vector Control. And by injecting a reactive or inert gas into the exhaust stream, you can change the direction of the thrust in a really binary way. Isn't that crazy? And then finally, we've got, this is the Vector Bravo system from Florida Tech, and this is a thrust paddle approach where you put small paddles into the exhaust stream in order to deflect the thrust. So the point of all of these things is to just change the direction of your nominal thrust, right? And I'm being really exhaustive with covering all of this stuff. But the next question you might have is, okay, cool, so I want to do this on my rocket, and I saw that dude who carbonated milk online was able to do it, so I can obviously do it. Yeah, I'm sure you did. I'm sure everyone saw it. It's going to haunt me forever. So how do you do it at the model scale? Well, my first advice is to start small. I've gotten a bunch of emails from folks who they have the right intentions and they say, hey, I really want to try this stuff, but I've got an M motor that I want to work with, right? And I want to rip on up to 50K with TVC. And how do I put this in the nicest and most gentle possible way? The first time that you try to do something like this, the likelihood of it going exactly how you want is somewhat low. This one looks okay, but so my advice is to start small so that when this happens with an F motor, it's a lot more forgiving than with an M motor. Now, I would aim for a vehicle mass of roughly 500 to 1,000 grams, just to talk specifics here. 500 to 1,000 grams is definitely within the low power class of model rockets, and then that's going to give you a great selection of rocket motors, and it's also going to give you a great selection of airframes. So 66 millimeter is a BT-80, 74 is a 3-inch tube, 98 is a 4-inch tube. These are excellent tubes to work with. I recommend going with the cardboard variant. You can work on fiberglass or carbon fiber or something like that, but with these weights and with the motors you have available, cardboard is a great option. And you're also going to be doing a lot of modifications to the tube, so I do recommend starting with that at the very least. And then finally, I would go for the gimbal mount. I'm not trying to tell you what you can and can't do, but liquid injection thrust vector control at 500 grams mass is going to be difficult, to say the least. All right. So that's how you can go about it. This is the way that I have approached it. This is the gimbal mount that I've done. So you're just gimbaling the entire motor. I've got 2 servos here. And this has similarities with Onions and Shrek in that it works in layers. So we've got the motor mount directly connected to that bottom servo, and that works on one axis. But then this top servo is sort of the outer layer of the whole gimbal, and it gimbals the entire bottom assembly, right? So we're decoupling these axes. But this is by far not the only way you can do it. My friend Rob, again, it's cut off a little bit. My friend Rob is an actual orbital launch vehicle engineer down in Cape Canaveral. He really knows what he's doing. But he's got a couple of different setups as well. So his thrust vector control approach uses it's not technically linear actuators, but it's actually quite close to how you would gimbal a liquid engine in that you've got these 2 orthogonal or 2 90 degrees apart rods that come down on the motor. He's also got a compliant gimbal, which once again, it's a little hard to see here, but it's a compliant gimbal means there are no hinges at all. It's all rubbery plastic that's hinging, so you don't get the degradation of any metal from exhaust products of the motor or something like that, which is pretty cool. For T0 systems is really great. And then finally, this is just a slide from last year's talk. I wanted to re-emphasize the importance of iteration here. It's going to be really hard, just kind of like the clips that I showed earlier of the failing rockets. It's going to be hard to get it right on your first try. And so if you're building something like this yourself, don't get too down on it. It's going to take a couple of tries to get it right, and it certainly has for me. And then this is a small little advertisement, but if you want any of these files, they are available for download on the BPS website. Okay, next up, how do you control this stuff? If you've ever flown model planes, has anyone here flown model planes? Cool, we got a couple of folks. You need a receiver, right? You need something on the craft that can talk to all of the control surfaces. And so we need something like that for a model rocket. You could have a Pixhawk. These are sort of all-in-one flight control systems. You can also have an ArduPilot, APM. All of these are cool options for model airplanes, but I don't recommend using them for model rockets. What you really want to have is full control over the software that's running on it and full control over the hardware that's going on it. And that's going to be the most efficient approach. So it's not too hard to do, and I wanted to start with a conceptual representation of what you need to do to build your own flight computer. I'm going to label this UC. U stands for micro and C for controller. U is the sort of subscript for micro, right? So in the very center, we're going to have something called a microcontroller, and that's going to run all of our code. Connected to that, we're going to use an inertial measurement unit, or IMU for short. That has a set of accelerometers and a set of gyroscopes to help us sense our orientation and where we're moving. We also need to sense how high above the ground we are, and that's going to be done with the barometer. You could do that with a LiDAR, and you could do it with a radar too, but it's going to be difficult to keep that pointed at the ground to resolve the altitude of your vehicle. Then we've got the bell of the ball here, the TVC servos. This is what it's all about. So these are going to connect to your microcontroller as well. This is pretty important. If they're not connected, they don't work. So you've got your thrust vector control servos, and the microcontroller is going to send all of the commands to them. Parachutes are non-negotiable. I am speaking to my former self here. Don't skimp on parachutes. You need a way to get your vehicle back, and you need a way to do it safely and responsibly. And if you don't, you end up hurting the hobby because of it. So we want to be making sure that we're doing this in a safe way and we can get it back. And so the parachutes are going to be controlled by the microcontroller. Obviously, you've got a battery connected to power all of these things. And then raise your hand if you've ever been in a field setting up a rocket and something has gone wrong and you have had to search for a dongle and then plug in your laptop in the bright sun and it has been a nightmare. Okay, well, no one's raising their hand, but I'm going to assume that some of you are familiar with the stress of being at the launch pad when not everything is looking okay. State indication, what I'm talking about here is buzzers and LEDs, something that you can really quickly get a sense for what's happening on my computer, what's going on, is everything ready to go. That's really important. And then finally, this is not technically required, but a data recorder is a really good idea for something like this. It is going to be extra work when you develop it, but it's going to pay off, I mean, in the most powerful way possible. Having data from your flight so that you can learn from it later on is really important. And so that might look like an SD card reader, that might look like a flash chip, something like that. And so let's now talk about the specifics of it. This stuff can get real boring real quick if you just say the numbers, so I'm going to try to keep it not boring. But we've got a bunch of different options for our microcontroller. We'll start off with the processor and the heart of the computer. What are your options when you're looking at this? You could start with a Raspberry Pi. These are really powerful computers. A BeagleBone is a similar setup, very powerful computer with a real-time operating system. You can also have an Arduino Uno. This one, I mean, I assume most of us are familiar with at least one of these boards in this room. A Teensy 3.2 is another excellent option. And then you could also go with a 8266, which is a Wi-Fi enabled board, or a Nucleo, which is an STM32 board. Okay, so that's a lot of numbers. The point is that you have many options when you're going through selection for what you want to drive your whole rocket. What's the primary MCU? I don't recommend going with the Raspberry Pi or the BeagleBone route. They're way overpowered for what you need, and honestly, the Teensy seems to be the best option. So just to reiterate here, if you wanted to pick from one of these 4 specific computers, these are all excellent options to choose from. We've got an Arduino Micro and an Arduino Nano, which are functionally almost the same. They're going to have slightly low processing power for what you want, but they will get the job done. The Arduino Zero is excellent too, and I have based a lot of my boards off of that same processor and schematic. And then the Teensy 3.2 is another great board that you just cannot beat the amount of processing power for the price and the footprint. Okay, now here we go. Is everyone ready for the rapid fire sensor suggestion section?
Let's do it.
Here we go. There's a lot of sensors you need, and there's a lot of options for them. So, inertial measurement units, what can you use? The Bosch B&O 055, the MPU 6050, and the LSM 60S3. These are all excellent options. These are all MEMS, IMUs, micro-electromechanical systems, which means they are cell phone grade. They fit in your phone. The B&O 055 is a little bit more expensive because it includes a lot of sort of microcode or micro software on board that helps you get the orientation of your vehicle, and the gyros and accelerometers are slightly higher quality. You do get what you pay for. But they're all roughly the same quality speaking. And they will all totally work for thrust vector controlled model rockets, at least at low power. Don't fly these on an M motor. Okay, for barometric pressure sensors, we've got the BMP 280. We've got the MPL 311582, and we know it, we love it. It's the BMP 180, right. All of these are, again, same quality here. They're micro-electromechanical systems, and they will all work just fine. Again, you can use a LiDAR, you can use a radar, and you will get more accurate data, but it will be really hard to get those measurements when your rocket is flailing around at Apogee. And especially if things don't go well, you don't want to sort of add to the failure cascade by knowing that if you flip out of control, you're not going to be able to get altitude. So for parachute deployment, raise your hand if you've ever done any type of project where you have had to switch a large amount of voltage or a large amount of current. Okay, good amount of people. What do you use? What do you use to switch that load? Oh man, okay. This didn't go as I had hoped. I was hoping you would say relay, so let's just pretend everyone say relay. Relay, of course, right? You use a relay. Can you use a relay on a rocket? Ready? No, do not do it. Don't use a relay on a rocket. Why not? Because it is an electromechanical device, which means it is a small physical switch inside, which is triggered by a solenoid or a little magnetic core, right? And so when you have a high vibration or a high shock event on a rocket, if you use a relay, you are at risk of triggering whatever's on the other end of that relay, right?
You learned that the hard way, Joe?
Oh, I definitely didn't learn that the hard way. No, I've definitely not learned that the hard way by slamming a rocket on the ground. I want to emphasize that one more time. I have definitely not used a relay on a rocket. Yeah, don't do this. Again, speaking to my formal self. So what do we use instead? A MOSFET, right? You can see this is the part of the presentation where I figured out the effects in Keynote. But yeah, MOSFETs are excellent options. They're sort of like digital relays. You can still switch very high currents and high loads with them, and you can do it without any physical moving parts, at least not at like the sub-micro scale. And so a MOSFET is an excellent option and a much better choice than a relay here. Relays are cool for like ground side stuff though. For launch pads, that's fine. You just don't want to put them on anything with high vibration or high shock. Okay, flight batteries. This part's really simple. What do you use to power your computer? You can use a 9-volt battery, but the current capacity on these batteries is a little bit low. They're not able to push out a ton of current. So, as an alternative, I recommend using a lithium polymer battery. And they're sort of like the bad boy of batteries, right? Like, you can get as much current and voltage as you want, but like, you might burn your house down. I recommend the lithium polymer approach. Just it's a lot stronger, and you're getting a lot more bang for your buck. So LiPos are great options. And then finally, for data recorders, you've got two major routes here. One of them is going with an SD card and writing directly to that. I don't really recommend this. If you're writing directly to an SD card, this is the same problem as the relay, right? It's an electromechanical connection. And so if something has high vibration or high shock in flight, you are at risk of either disconnecting your card completely or, I think worse, partially, and that will corrupt your data. So instead of doing that, I recommend something that solders directly onto the board, and that looks like a small flash chip. And sometimes they make little breakouts for them. You see the little I2C FRAM thing right there. Flash chips are great. Honestly, some processors might have enough EEPROM to just write to that, but a flash chip is a great alternative for that. And then you can write to an SD card on the ground. That's how a lot of my flight computers work. I write to the flash in flight to avoid errors with vibration and shock, and then when the rocket has detected that it's landed, we write over to the SD card so I can easily get that data at the end. Now, there are two main routes to assembling all of this stuff, right? The first one is a breadboard or protoboard. And this is sort of an open, this is like the millennial of approaches. It's an open concept, right? I don't know if that is a good joke, but the breadboard or protoboard is a great approach, especially if you're getting started with electronics and this is your first project or close to it. If you make a mistake with this, it's a lot more forgiving than the alternative, which is a printed circuit board. And PCBs come in a lot of different flavors. You can do them in a lot of different ways, but they are going to be lighter. They are going to be more space efficient, and you're going to have pretty much total control over how your schematic looks. But if you don't yet have a schematic, a great way to figure that out is a breadboard or a protoboard. And I've flown, I think the first year and a half or 2 years of my rockets, and some of which were successful, many of which were not, but some of which were successful were breadboards and protoboards. So it totally works. And it's a lot more forgiving to get started that way. All right, software. This is one of two things that I get a lot of questions about. The project has a decent following at this point, and so there are a lot of people who want to know, how do I write my flight software? How do I do it? Now, not everyone here, I mean, how many people in here know how to code? Again, probably a bad question to ask. I was hoping for fewer. The point is that software, when you show the actual code, if someone doesn't know how to code, it's not as intuitive. And so I wanted to talk about how you set up your software scheme from a high level. And that can help you get sort of a roadmap for how you might go ahead and set it up at a low level. All right, so let's start with, again, oh boy, this is going to be harder with the screen cutting off. So let's talk about what's called a state machine. And a state machine works, I'm going to simplify a lot of things here, but a state machine works by chunking code into different sections. So we have 6 different sort of sections or states in our flight right here. We've got ground idle on the launch pad, powered flight, which is when we're under thrust vector control. We've got unpowered flight, which is after TVC has stopped, after the motor has burned out and we're still coasting up. Ballistic descent is when we are past apogee and not yet under chutes. Chute descent is when we're under chutes, and then finally landing / safe state. And the big thing with state machines is they simplify a lot of your code. I can run just one section right here for powered flight, just one section of code, and then all of the stuff that's related to that, I don't have to run any other time. So it's going to simplify a lot of how I write that out. And the big thing is, how do you get between them? How do you do those state transitions? So I wanted to take a look at how you do the state transitions between all of these. And this is really like a core thing that has helped my software stay at least somewhat simple. So when you go from ground idle to powered flight, what does that transition look like? It's liftoff, right? If we can detect liftoff, we know to switch to the next section of code. From powered flight to unpowered flight, again, pretty simple. It's just burnout. A lot of these things are not super complicated, but I wanted to be sort of exhaustive with the approach here. From unpowered flight to ballistic descent is Apogee, right? If we can detect Apogee, we know we're no longer in unpowered flight, we're now descending. Pyro fire, when we fire one of those parachutes, that's when we switch from ballistic descent to chute descent. And then finally, for detecting landing, this one can be a little tricky, and there are a lot of approaches. I'm not saying this is the right one. But if we were to detect that we were less than 5 meters above ground level for maybe 10 seconds, if we can detect that, we can be pretty sure that we've landed on the ground. So this is sort of a general approach to it, and I wanted to take a closer look. Let's take a look at how you detect that you have launched. We have a z-axis accelerometer, which senses the longitudinal axis acceleration, the long axis, right? And we say, if it's greater than or equal to some threshold, we must have launched, right? We're going to be under acceleration right at liftoff, and so this is a quick way to detect that. We can either go yes or no. And if it's no, if we haven't gone past the threshold, we do nothing, right? That's pretty easy. But if it's yes, we don't necessarily switch into the launched state yet, because what happens if I just drop the rocket on the ground by accident? I don't want to, but if I do, that's an acceleration spike, but it's not a launch, and I don't want the rocket to arm. So we can do a small piece of logic here that just takes a little count to 0.1 seconds. And if we have been above the threshold for 0.1 seconds, if that's a yes, then we know we've launched, right? Does this make sense? OK, cool. Just wanted to make sure. Yeah, so if it's above 0.1 seconds, if we pass both of these tests, then yes, we have launched. If no, then don't do anything. OK, so that's just a state transition. That's just walking through it. How do we do it for burnout? Well, it's pretty much the same thing in reverse, or in the opposite. So if the accelerometer is less than or equal to, I'm going to get more specific with the threshold. I have it set up as 2 meters per second squared in my software, and this is a great range above 0. So when the rocket burns out, we're going to see 0 acceleration on almost all the axes, or close to it. And so I just set the threshold there. But if we are less than or equal to 2 meters per second squared, great, we can start the counting process. If not, do nothing. And so this is the same thing here, just writing it out. The slide was a little bit slower than I anticipated. Right, if we do no and we do nothing. If we do yes, we have MECO. This is actually used on a real orbital launch vehicle. Do we know which one it is? Does anyone have any guesses? Like I would bet something very, very close to this is used on a real orbital launch vehicle.
Falcon 9.
Not the Falcon 9. It's kind of like it, though. Not the Antares. Might be the Antares. So I think
Without Atlas 5.
Atlas 5, no. Think small. Oh, someone had it. Electron, yes. So the Rocket Lab Electron uses electric turbopumps, right? And that means, I am pretty sure, don't totally quote me on this, I'm pretty sure they burn their tanks completely to depletion instead of having a low propellant sensor. And when they do that, they don't actually have control over exactly when their vehicle burns out. So on the stream, you will hear them call out burnout detect mode. You'll hear the flight director call that out, and that's when the vehicle is switching into a new state. A lot of launch vehicles do use state machines as well. And so it switches into a new state where it's looking at probably something like this to detect when it has burned out and then start the stage step sequence. OK, how do you detect Apogee? Or no, yes, that's what's next, sorry. All right, so how do you detect Apogee? This is my expertly drawn, incredibly beautiful depiction of a rocket's flight, right? So we lift off on the left and then we land on the right, and we have Apogee in the middle. Now, let's say that our rocket is at Apogee. And what we do to detect apogee, to figure out if we've passed that, is we compare two different readings that are 1 second apart. You can use any length of time for this, but I'm going to say 1 second for simplicity. If I'm at apogee, which we'll call 30 meters, and I look 1 second ago and we were at 25 meters, if 30 meters is greater than 25, we must be ascending or at apogee or close to it, right? And in the same vein, if we are at let's say 25 meters going down, and the last reading 1 second ago was 30. If that reading is greater than the reading 1 second ago, we must be descending. And we can set this up as an easy if statement here. Again, using just sort of pseudocode, if the current altitude is greater than the altitude minus 1 second, the altitude 1 second in the past, we must be ascending. And the thing we're really interested in here in detecting apogee is if the current altitude is less than the altitude 1 second ago, we must be descending. Are we all on board? Everyone good? Okay.
Like using velocity or acceleration?
You can use velocity and acceleration too, but especially as your flight profile gets larger, it's difficult to rely on that. I don't know what scale of rockets you fly, but if you use acceleration, especially with the MEMS quality of sensors, sometimes it can be hard to figure out exactly where apogee is. So I think this is a more robust approach. And since detecting apogee in software like this isn't extremely time sensitive, I like this approach. But again, I don't know if I've emphasized this enough, but there are no right answers here, right? This is just a suggestion for how you can do it. Okay, what's next? We have to detect if the parachutes have come out. And more accurately, I'm just going to detect if we fired the parachutes. This one's pretty easy. So how do we fire those parachutes, but only on the way down? If we look at each part of the flight here, we first have, this is another expertly drawn flight curve here. We've got the thrust vector controlled section, then we have unpowered flight, we have descent, and while we're in the descent mode, we start running a little bit of code that just says, hey, if we are less than or equal to 25 meters, or whatever we want to set for chutes out, if we're less than or equal to 25 meters, fire those chutes and then switch states to the chute descent state. So this is a great example of why, here we go with the drawings. I got carried away. This is an excellent example of why the state machine is so powerful, because if I were to run this code in any other section of flight, it would not work well. And in fact, if we were to run the code that says if we are less than or equal to 25 meters in some of the early flights, I would be deploying chutes on the way up, and the flight would be curly, to say the least. All right, and then finally, how do we detect that we have landed on the ground? Here is the ground. This is the path of the rocket. Here's the rocket on the ground. Really went all the way with the drawing, and then I drew the sun. Anyway, this is the same thing I outlined it earlier, but just wanted to drive it home. If we're less than 5 meters for maybe 5 seconds or so, or 10 seconds, we can detect that we've landed. Now, after drawing this, I thought about it harder, and I was like, wow, there are like 1,000 ways you could detect landing. Technically speaking, you could detect it by looking only at the gyroscopes. You could see if there's just no movement at all. When you're under parachutes, you're always going to be rolling or moving in some way. And so you could look at the gyroscopes to see what the standard deviation is on those over a period of 10 seconds. You could look at, you could look at the altitude as well. You could look at the accelerometers to see if one axis or two combined axes show 9.8 meters per second to sense gravity. Although that's a lot harder because when you're under chutes, the acceleration is going to be very close to that. Anyway, the point is that there are lots of ways to detect these types of things. So what next? If we have our basic flight software, I said earlier that software was one of the things that people ask about a lot, and it was one of two things. What is the second thing? My 3 favorite letters, GNC, guidance, navigation, and control. So anyone who flies rockets, which should be all of you, know why these rockets shouldn't fly, right? They don't have fins, or more specifically, they do not have aerodynamic stability. When you look at these things, they are just big, long sticks. And so guidance, navigation, and control, the people who work on that, are responsible for keeping these things straight up or pointed in the right direction and heading to the right place. And this footage is just excellent. Clear day launches are like the best. And when we talk about GNC, one of the things that people love to talk about too is the Falcon 9 landing, and of course had to include some footage of that. And I figured what we could do today is talk about how the Falcon 9 landing algorithm works. So let's do that here. When the Falcon 9 lands, or more accurately, when it's in the air, it is using an algorithm called GFold, which stands for Guidance for Fuel Optimal Large Diverts. And to give a really quick and simple explanation of what GFold is, the GFold algorithm solves the fuel optimal and minimum landing error problems by using an equivalent convex relaxation of the non-convex spacecraft control constraints. And in fact, the successive convexification of a lot of these algorithms is what allows you to have that non-convex approach to your control constraints. So are we all on board?
Say that again.
Just one more time, slower. No, okay, so I understand about a third of this, so we can't talk about this today. And I figure what's probably better is just keeping a rocket upright. This is unsurprisingly much easier than trying to land from space. And so we're going to do this again with a conceptual representation, and I think this will help in the long run if you have no familiarity with this type of stuff. So I'm going to draw a box, and I'm going to call that box rocket. You can guess what goes on there. In this box, there is an input and an output. We know what we put into it, and we know what we get out as a result. This is a black box. We don't necessarily know what goes on inside of it. And again, this is just all conceptual, but what goes into it is going to be torque. And torque is a twisting force that we can put on the vehicle to turn it one direction or the other, right? We're just talking about the force here. As a result, the rocket box is going to spit out a number, and that number is going to be angle. So we're going to put in torque, and if you want to be specific, we could put in torque in Newton meters or pound feet, whatever you want. And angle is just going to be in degrees. All right, are we all on board? Simple enough. We've got a box that turns torque into angle. Next up, I'm going to draw a box next to it, and we're going to call this box TVC Mount. Yes, Mount. This box is going to be similar to the rocket box, and it's just a conceptual representation of how the rocket works. In the input for the TVC mount, we're going to have a command, and that command is just going to look like an angle in degrees. So I tell this box, hey, go to 5 degrees, and then the TVC mount represents what happens when I tell that mount to go to 5 degrees. Maybe it represents the little delay of the servos. Maybe it represents a little bit of misalignment or something like that. And then out comes torque. So we can just connect these boxes up. Are we all on board? We get a command that comes in to the TVC mount, and then we get the sort of force or the twisting force that comes out of there. It goes into the rocket, and we get a resulting angle. So we're sort of constructing what you might call a loop. And how do you control this system? Does anyone have any suggestions? Magic is close, but not right. What if I took a little line and I went like this? Whoop, and I just connected them up. So let's run it through, right? We've got an angle. Let's say the angle is 5 degrees on the rocket. And the 5 degrees goes all the way back to the TVC mount and now commands the mount to go to 5 degrees. So the rocket is pitched over, and now the mount is pitched over as well. When that happens, we get a torque on the vehicle, and the torque starts to correct the rocket. So now the rocket is at 3 degrees, and we come back, we go into the TVC mount, we're closer to upright, we're closer to 0, and so we don't need as much torque, which is great news because we've commanded less of it from the thrust vector control mount. And then finally, when the rocket is at 0 degrees, we run that back, and we command 0 degrees from the mount. So nothing has changed. We are perfectly, we're in agreement, right? So this would be a stable system. Well, what happens if I fly this with a really light rocket, and I fly it with, and I'm one of the people who emailed, and I'm using an M motor. If I fly this with a rocket that's 500 grams and I use an M motor, what's going to happen? It's going to overcorrect quite a bit, right? And maybe that example was a little too crazy, but if my rocket is lighter, how do we control it? Let's take this line out, and I'm going to draw another box. We're going to call this box P. Don't worry about what it stands for. I'm sure it's nothing. That P box is just going to be a multiplier of whatever comes into it. And that multiplier is going to be 0.5. So when we send the angle in, let's say the angle is 10 degrees, what are we getting out? 5, right? If the angle is 3 degrees, what are we getting out? 1.5. And if the angle is -6, -3. It's directly proportional, you might say, right? So that's what the P stands for, is a proportional gain. Whatever the angle is, the command is a proportion of it. So now we can sort of dial in, how strong do we need these correction forces to be because we've got proportional control. Okay, now let me give you an example that is separate from rockets. Let us say that you are in a parking lot. It's like a totally empty parking lot, just so we're safe. You're at one side, and on the other side is a parking spot that you want to be in. You're in your car. And you know that you're really far from the parking spot, so you jam on that accelerator. You go all the way, pedal to the metal, and you start accelerating. And you're speeding up, and you're just using proportional control in this situation. You want to get to that parking spot. Now you're halfway across the parking lot. You're doing a buck 20, 120 meters per second through this parking lot, and you are still on the accelerator, even though you are quickly approaching at a speed that can be represented by a Mach number. You are quickly approaching that parking spot. And even when you are 20 meters from the spot and doing like an unconceivable speed, you are still on the accelerator. And that is exactly what we're talking about here, because what we don't have in this control system is a brake, right? When you brake in your car, you are not controlling the position directly, you're controlling the velocity. So that's what's happening, you're changing your velocity. So in the parking lot scenario, you get to halfway across the parking lot doing several hundred miles per hour, and you start to think, I might need to put on the brake now. So we need something like that in our system. And how do we set this up? Well, I'm going to draw some lines here, and then we're going to explain what they mean. First, I'm going to put another box in here, and I'm going to call this box D. And don't worry what it stands for. I'm, again, sure it means nothing. From this D signal, we're going to put a little bit of math right here, and I'm just going to say dx over dt. And that represents what's called the derivative of the angle we send into it. So the way this works is the angle, it's going to come in, something's going to happen with that derivative, and I'll explain that in just a second. Then it's going to get multiplied by 0.1, and then it's going to go back into the system. So what does the derivative do? The derivative, let's break down what dx is. Dx stands for delta x, which is change in x, and then that is over the delta t, which is change in time, right? So if we have the change in our input value over the change in time, that's velocity, right? If our input value in the car scenario is position, if we take our position at 1 second and our position at 2 seconds, and then we divide by the change in time and the change in position, we get our velocity. And that's exactly what we're doing here. So if we got an angle of 5 degrees, one control loop, and then we got an angle of 10 degrees, a second later, we're going, 5 degrees per second? I think I made that up. I'm pretty sure that's right. It's hard to do math during a presentation, but basically we're getting the angular rate, the angular velocity through this dx over dt. And when we send it through this, the angular velocity turns into a command, right? We multiply by 0.1, we have a command of correction. So let's give a quick example of this. Let us say that the rocket is at 2 degrees. Okay, it's 2 degrees pitched over, and we still want to be pointed upright, right? So I have 2 degrees on the angle, and then when we send this back into the p gain, we're going to get, that's what this is called, by the way, is a gain. These multipliers are called gains in control systems. When we multiply this by 0.5, we get 1. So we have a 1 degree deflection on the thrust vector control mount. But we are very close to 0 angle, so we don't need a lot of correction, but we are moving very fast in this scenario. Let's say that we're actually moving at like 20 meters per, not 20 meters per second, 20 degrees per second. And so when we do the derivative of this number, we're going to get that 20 degrees per second angular velocity. And when we multiply that by 0.1, we're going to get 2 extra degrees that are added into our thrust vector control mount, and that is our brake. That's our brake to slow the rocket from pitching so fast. And to be clear, 20 meters per second is what, like, it's not very fast. But we have a brake in our system now. Does this make sense to everyone? We've got a bit of a braking gain. And now I want to add one more thing. This one is one that can really ruin your control system easily, but let's go for it. I'm going to add another term here, an I, and again, I'm sure it stands for nothing, right? The I value is going to be 0.2, and we're going to draw a little squiggly guy right here. This squiggly guy represents something called an integral, and then we're going to connect this all up to the system, just like we did with the box that represents the derivative of the control system, right? And so this integral I think the best way to describe this, first I'll just say it adds up everything that comes into it. So if we have the rocket at 5 degrees, or let's say if we have the rocket at 2 degrees at one time step, at one point in time, that's going to go into the integral, and the integral is going to be 2 degrees. But then if at the next point in time the rocket is at 3 degrees, now the integral is 5 because it's 2 plus 3. And then if at the next time step we're at 4 degrees, now the integral is 8 because we're adding these all up. And this works in the negative direction too. If we had a degree of -4, we'd go back to 5. All right, this is all fairly simple, but then that gets multiplied by an 0.2. So why do we need this here? Well, when you build your thrust vector controlled rocket, you are not going to get it perfectly built every time. And in fact, you're never going to get it perfectly built. It's an impossible standard that you won't be able to hit. So what we do is if the mount is slightly, let's say the mount is slightly misaligned by like 1 degree. You missed it in calibration and it's just there. When the rocket launches, it's going to be arcing over just a little bit, but those P and those D gains are going to correct for it. But you're going to stabilize around a point that is probably closer to like 1 or 2 degrees, right? Regardless of whether, like what those actual values are, you're not going to end up as a straight upright point, because when the mount actuates to get rid of that misalignment, your vehicle is going to be tipped over. And the control system, if I get rid of the I, the control system has no way to correct for that. And so the I term is adding up all of that error over time. If we're constantly at 1 degree and stable, that I term is going to add up that error and be like, wait a minute, we're not at 0. So it's that 1 degree is going to accumulate over time, and multiplying it by some gain lets you dial in how fast you want the system to correct for its own inherent errors. So that's how fast you want the rocket to correct for its own inherent errors. And you can see through just a little bit of thought here how this can just go way out of control really quickly. If this value for I is way too high and we have the rocket over with an integral of like 5 degrees or something like that, you're going to start correcting like crazy, and it's going to fishtail everywhere. So the I gain is something to be really, really careful of. And so that, if you hadn't figured it out like a long time ago, because it was pretty obvious, but this is a PID controller, a proportional integral derivative. And so hopefully this helps. Usually when people describe PID controllers, they don't talk directly about rockets. And this would have helped me a whole lot when I was getting started. So that's a PID controller. And I know for a fact there are at least a positive number of launch companies that do use direct PID controllers to guide their rockets into space. Not everyone does. There are a lot of approaches for this, but a PID is how you can keep your rocket upright. Okay, so we've covered what thrust vector control is. We have talked about how you can use it. We've talked about a whole lot, and I have missed a whole lot as well, because there's a finite amount of things that I can fit in about 40 minutes, or however long it has been. So I didn't talk about tuning the rocket. You know, how do you find those gains for the PID controller? That's one of those things that it's going to be really helpful to build a simulation offline that simulates the physics of the object. And then, you know, how do you actually write the code? Well, there are a lot of great tutorials online, but no one's going to tell you exactly how to do it. So there are a lot of things that I didn't cover here, but I hope this helps, and I hope this is like a good roadmap for someone getting started. That was my goal here. Hopefully I have accomplished it. So thank you very much for joining me today. Thanks for Narcon for having me. And if you have any questions, I would love to chat. Question? Yeah?
You use your automatic approach for thrust vectoring, but in a lot of model rocket flights, a good part of the ascent is unpowered, coasting. Have you experimented with maybe actuating fins or rudders?
Yeah, I'm getting there. So, okay, so first, the initial goal with the thrust vectoring stuff was not necessarily to go high and fast. It was to sort of simulate the low and slow like liftoff that most of the real orbital launch vehicles get. But of course, like that doesn't, if you're working at the small scale, it's not necessarily that impressive, right? And so a lot of model rocket flights do have instability after burnout if they don't have the right amount of fin stability. And that's just a physics thing. I unfortunately can't fix that. But I am experimenting with a couple of things. Gary from Aerotech has built in the last year an H13 motor, which burns for like 16 seconds or 14, something like that, with an average thrust of 13 newtons. And I have a rocket called Sprint, which has very small fins that shift the center of pressure to exactly the center of mass, so that it may not be exactly stable, but essentially my goal is to go as high and as fast as possible. And I'm pretty sure I can get to at least 1 kilometer with it. That's the goal coming up. Basically, to answer your question, fin control, I would like to try that this year. It's very difficult because you have to have a really good characterization of how your airfoil works at a lot of different speeds. So your control system has an extra step over if you command a certain torque on the vehicle. It really depends on how fast your free flow airspeed is. And then, I mean, yeah, there are a lot of ways to approach stability. And frankly, if you wanted to add fins, you could do that too, and it would just be stable after burnout. Yeah. Sure.
You're going to reintroduce your kits?
Yeah, the signal kits come online roughly once every 6 months at this point. I really would love to have them constantly available, but as one person working out of my living room, it's very difficult to keep everything like development-wise afloat and also, deal with shipping out orders. I'm still trying to work toward a solution where we can keep them online indefinitely, but I don't have.
Keep watching for releasing.
Yeah, and I'll be real clear about it all over the the BPS social media channels. So Instagram, Facebook, Twitter, whatever. But I think sometime this spring we should have another release of the kit. Yeah.
Hey Joe, you've been playing with cold gas vector control.
Yeah.
Where's that now, and where's it headed?
So I built a reaction control system in last spring / last summer, and it actually started working really well in the ground, and then I hit a couple of different snags. So the first problem was I could not get the flow rate, the mass flow rate that I wanted from the valves that I was using. If you don't pay a lot of money, it's really hard to get a very large orifice in your valve that actuates really, really quick. And so it was difficult to find valves that would suit those needs. And then I also, I didn't talk about this at all here, but in the last 6 months or so, I have rewritten all of my guidance and control software. So I had been building, this is actually why I stopped doing the landing test but of the Echo vehicle too. I stopped doing those tests because I realized I'm building on a lot of the stuff that I wrote in 2017, which at this point is 3 years ago, and I realized I need to be revamping how I do GNC. And so if any of you have seen what's going on with BPS right now, I've got this hopper vehicle called Sprite, and the whole goal of that is much more precise guidance, navigation, and control. And I don't have any videos of it right now, but if you look at them online, it's getting really, really stable, and that's all the revamping of control. So that, in a very long form, is why I stopped the RCS and a few other projects. Is I realized if I double down and take a few months off of flying, I can come at this with a much better approach in the future. And I did get offers for a couple of those really, really fancy valves, but I just didn't have the control software to support it yet. Yeah.
What's your gas source?
What's my gas source? Paintball tanks right now. And CO2 would be really a much better choice because of its density. But there are a lot of gases that are more dense, but CO2 in terms of safety is pretty good. But just on the ground, I was testing with air, compressed air, yeah.
And you have less temperature variability.
Yeah, exactly. You have to be careful with your valves if you're sending a lot of flow through them with CO2. You got to get real cold real quick. Yeah. Sure.
Joe, just a comment. There are those of us in this room who've seen all of your presentations.
Oh, great.
This has been huge fun to watch this growth and progress.
Oh.
So thank you so much for coming every year.
Yeah.
Well, thank you.
That
Yeah.
This is not the Netflix version where we stream the whole thing at once. You have to come back for episodic, but it's just been absolutely wonderful. Thank you.
Yeah, thank you so much. It's really easy to just show all the videos here, and I that was what I was going to do. You'll notice the presentation is titled BPS 2020, because when Bryce asked, what do you want to do, I was like, oh, I don't know. And I figured only in the last 2 weeks, I realized what I want to do is I want to lay out a map so that if I were getting started right now, how would I do it? And all of these things would have helped me so much and saved me a lot of time.
Is your second presentation just a
Yeah, the second one will just be a repeat of this, I think. Yeah.
What is BPS?
Okay, so the question is, what does BPS stand for? This is a lesson. BPS stands for Barnard Propulsion Systems, and my name is Joe Barnard, so that makes sense. Here's the thing, though. I build every single part of the rocket except the propulsion system. I kid you not. So the lesson here is don't name your business. Don't name your project or business before you really know what's going on. When I got started, I mean, VPS is, I guess, sort of an example of like how little I knew when I got started. Because I was like, yeah, propulsion is a rocket thing, right? So, yeah.
Your BCS.
BCS, Barnard Control Systems. Yeah.
Subsidiary of BPS.
A subsidiary of BPS.
Joe, it's safe to say from people's reactions and from what Steve just said, you know where you're going to be this time next year, right?
Oh, yeah. No, I'm coming back. Yeah.
At the next Narcon.
I love Narcon, man.
All right.
Yeah.
Awesome.
All right. Well, anyway, folks, there is another presentation later in the day. And so maybe I'll see some of you back here. And if not, thanks for coming.